Somewhere in Boulder, Colorado, in a low building that from the outside looks like it could belong to any government agency doing any unremarkable kind of work, there is a clock unlike anything in your house, unlike anything you have likely encountered anywhere in your life. It sits in a room held at a precisely controlled temperature, mounted on a platform engineered to absorb vibration, connected to systems that actively compensate for fluctuations in humidity and atmospheric pressure, and stray electromagnetic interference from the surrounding environment. It has no hands. It makes no sound you could hear. What it does in a way that should rearrange something fundamental in your understanding of how the universe works, is count the oscillations of a single aluminum ion suspended in an electromagnetic trap, cooled to within a tiny fraction of a degree of absolute zero, probed by a laser, tuned to a frequency so exquisitely precise that the word precise begins to feel like an insult applied to it. When this clock was built, in 2010, it was accurate to approximately 1 second in 33 billion years. The universe itself is only 13.8 billion years old. If the universe were more than 2 times older than it currently is, this clock would not yet have drifted by a full second. Subsequent clocks built with ytterbium and strontium atoms have since surpassed even that precision, reaching accuracies of 1 second in hundreds of billions of years. Human beings, it turns out, are extraordinarily good at measuring time when they decide to take the project seriously. I tell you about this clock not to impress you with engineering, though the engineering genuinely deserves more admiration than it usually receives. I tell you because in 2010, the scientists who built this clock did something that should have been on the front page of every newspaper in the world, and was instead reported primarily in journals and covered briefly in science blogs before the news cycle moved on. They took 2 of these clocks, 2 of the most precise timekeeping instruments then in existence, and placed one of them on a shelf. They placed the other on a different shelf, 33 centimeters higher, a little over a foot off the ground. They let both clocks run simultaneously and measured the difference, because there was a difference. The clock placed higher ran measurably, reproducibly, actually faster than the clock placed lower. The difference was a fraction so small that writing it in decimal form would require 17 zeros between the decimal point and the first significant digit. But the difference was real, it was repeatable, and it was exactly, to the precision available, what Albert Einstein's general theory of relativity had predicted would happen, in equations he wrote down in 1915, more than 90 years before atomic clocks, sensitive enough to test this, existed. 1 foot of height difference on the surface of the Earth changes the rate at which time flows. This is not metaphor. This is not analogy. This is a measurement. Let your body find its weight wherever you're lying tonight. The mattress, or the couch, or the floor, whatever surface has agreed to hold you for this particular night, is doing the quiet work of supporting you against the downward insistence of gravity, the same gravity that makes the clock on the higher shelf run faster than the clock on the lower one. Let that work be done. Let the surface take you. And as you settle, I want you to carry something into the next 2 hours. Something that took me a genuinely long time to absorb, in the way that facts have to be absorbed before they stop being information and start being felt. The floor where you're resting is experiencing time at a very slightly different rate than your ceiling. Not enough to notice, not enough to matter for anything practical, but actually, measurably, physically different. And if instead of your ceiling, you were a mile above your house, or 10 miles, or 1,000, or orbiting at the altitude of the International Space Station, that difference would grow. And if instead of 1,000 miles above Earth you were near an object of truly extreme gravity, near a black hole, where the escape velocity equals the speed of light itself, the difference would not be measured in fractions, invisible to any instrument. It would be measured in years, in decades, in the span of a life. Tonight we are going to follow time to its most extreme edges. We will find the places in the universe where it slows to a crawl, where a single afternoon experienced by one person corresponds to decades lived by another. We will stand at the edge of a black hole from two irreconcilably different perspectives, one from outside and one from within, and discover that both perspectives are valid, that the universe maintains both stories simultaneously, and that these two stories cannot quite be stitched together into a single coherent timeline by anyone. And we will arrive at what I consider to be the strangest and most quietly extraordinary thing in all of modern physics: the person falling into a black hole, crossing the event horizon, vanishing forever beyond the boundary from which nothing can return, feels nothing. At the moment of the most radical transition that physics can describe, at the one-way threshold past which no signal, no light, no information of any kind can ever travel outward, that person experiences nothing unusual at all. Albert Einstein published 4 scientific papers in 1905. He was 26 years old, had not yet completed his doctorate, and was working as a patent examiner in Bern, Switzerland, reviewing applications primarily for electromagnetic devices, equipment that transmitted signals across distances, and required him to think carefully about what it means to synchronize 2 clocks in different places, about how information moves from one location to another, and what assumptions we make without realizing it. That work was almost certainly feeding something in the background, because in those 4 papers, the conceptual structure of physics changed permanently. The one that opens tonight's story is the special theory of relativity. Special relativity rests on 2 postulates that sound almost too simple to carry the weight of everything they imply. The first, the laws of physics are the same for all observers who are not accelerating. Whether you are sitting still or moving at any constant velocity, the physics you observe behaves identically. The second, the speed of light in a vacuum, is the same for all observers, regardless of how fast they or the source of the light are moving. That second postulate is where everything changes, because it violates a deep intuition that works perfectly for ordinary objects. When you throw a ball from a moving car, the ball's speed relative to someone standing on the road is the speed of the car plus the speed of the throw. That arithmetic works for balls and for cars, but light does not obey that arithmetic. A beam of light emitted from a spacecraft moving at half the speed of light does not travel at 1.5 times the speed of light relative to a stationary observer. It travels at exactly the speed of light. This is not approximate, not a useful fiction, not something that breaks down under closer examination. It is what the universe does. The mathematics required to reconcile that constancy with the rest of physics, to keep the speed of light fixed for all observers regardless of their relative motion, is called the Lorentz transformation, and what it shows is that time itself cannot be fixed. If the speed of light must remain constant for all observers, something else must accommodate the constraint. What accommodates it is the rate at which clocks tick. A clock moving relative to you ticks more slowly than your own clock. Not because of any mechanical defect, not because of vibration or wear, or anything correctable by a watchmaker. The moving clock ticks slowly because time itself is passing more slowly in that clock's reference frame, relative to yours. When the moving clock eventually slows and returns to your location, it will show less elapsed time. Real, actual, unrecoverable less time. If that clock were a person, a twin aboard a fast spacecraft, that twin would come back genuinely younger, not feeling younger in the way a good night's rest makes you feel young. Actually, biologically, measurably younger. Then in 1915, Einstein completed a second theory, general relativity. Where special relativity handled constant velocity motion, general relativity incorporated gravity and acceleration. Its central claim is one that, stated plainly, feels like someone has quietly removed the floor from under your most foundational assumptions about the world. Gravity is not a force. It is curvature. Mass and energy bend the 4-dimensional fabric of space-time. the three dimensions of space woven together with the dimension of time. And what we experience as gravitational attraction is simply the tendency of objects to follow the straightest available paths through that curved geometry. And because time is one of the dimensions that gets curved by mass, clocks sitting deeper in a gravitational well, closer to a massive object, run more slowly than clocks sitting higher up. Not slower in a mechanical sense, slower in the sense of genuinely having less time pass per second, as the universe itself reckons it. Time is not a neutral backdrop. It is a physical thing. It bends. There are currently more than 30 operational satellites in the global positioning system. The exact count varies as older satellites are retired and newer ones launched. But the constellation is designed so that at least 24 are in useful orbits at any moment, ensuring that at least 4 are visible from any point on Earth's surface simultaneously. Each satellite carries atomic clocks synchronized to a global time standard. When your phone determines your location, it is receiving signals from several satellites at once, comparing the timestamps on those signals and using the tiny differences in their arrival times to triangulate your position. The calculation assumes the signals travel at the speed of light. It also assumes the satellite clocks and ground-based clocks are synchronized. And here is the thing that should make you stop. Without explicit relativistic corrections, GPS would fail. Not gradually or subtly. It would drift by roughly 10 kilometers per day. A week of uncorrected operation, and your navigation app would show you 11 kilometers from where you actually are, and the next morning 22, and the next 33, growing without limit until the entire system was useless. The failure comes from two simultaneous relativistic effects working in opposite directions. The GPS satellites orbit at an altitude of approximately 20,200 kilometers, deep in the Earth's gravitational influence, but meaningfully higher than the surface. Being higher up means operating in a slightly weaker gravitational field, and general relativity predicts that clocks at higher gravitational potential run faster. For the GPS satellites, this gravitational effect causes their clocks to gain about 45.9 microseconds per day relative to clocks on the ground. But the satellites are also moving at roughly 3.9 kilometers per second, fast enough that special relativity predicts their clocks run slow due to velocity. That velocity effect causes a loss of about 7.2 microseconds per day. The net satellite clocks run fast by approximately 38.4 microseconds per day. A 38 microsecond drift, accumulated in navigation calculations that assume perfect synchronization, translates to roughly 10 kilometers of positional error per day. To compensate, the satellite clocks are physically adjusted before launch, deliberately set to tick slightly slow, at the rate they will show once both relativistic effects are acting on them in orbit. The adjustment is engineered from Einstein's equations. Your phone is using those equations right now. Every map application, every navigation system, every location-based service you have used today was built on the foundation of a theory that begins with the constancy of the speed of light and ends with the curvature of space-time by mass. Relativity is not academic. It is infrastructure. But what I want to draw your attention to is something slightly different from the engineering itself. The GPS correction exists because the effects are large enough, at orbital altitude and satellite speed, to render a navigation system useless within days. The satellites are not moving particularly fast. 3.9 kilometers per second is less than 1/100% of the speed of light. The altitude of 20,000 kilometers is deep within Earth's gravitational sphere of influence. These are modest extremes, and yet the relativistic effects accumulate to 10 kilometers of navigational error per day without correction. The same physical mechanisms, taken to their logical extreme near a neutron star or a black hole, do not merely require a correction, they become absolute. At the event horizon of a black hole, The time dilation factor does not require a small adjustment. It becomes infinite. In 1959, Robert Pound and Rebka, working in the Jefferson Physical Laboratory at Harvard University, measured gravitational time dilation inside a building, not near a neutron star, not at a black hole, in a building. The experiment they designed was ingenious in its directness. They placed a source of gamma rays in the basement, a sample of iron 57, a radioisotope that emits gamma rays at a very specific, very stable frequency when it undergoes a nuclear transition. They placed a detector at the top of the building, 22.5 meters above. They tried to detect the gravitational redshift of those gamma rays as they climbed that height against Earth's gravity. The expected shift was tiny, approximately 2.5 parts in 10 to the 15th power, a fractional change so small that most measurement techniques of the era couldn't touch it. To achieve the required sensitivity, Pound and Rebka used a phenomenon called the Mossbauer effect. By moving the gamma ray source at precisely controlled velocities, they could introduce a Doppler shift that scanned across the exact frequency range where the gravitational shift would appear. This allowed them to detect the shift not as an absolute measurement, but as a comparison between the shifted and unshifted signals. The experiment worked. Their result matched Einstein's prediction to within 10%. In 1965, Pound, working with Joseph Snyder, refined the measurement to within 1% of the theoretical prediction. Time ran measurably, detectably faster at the top of a building than at the bottom. Not in a way that would accumulate to anything noticeable in a human lifetime, but measurably, in a building you could walk around, using equipment transported up a staircase. But what should stop you? What stopped me, when I thought about it carefully, is not the smallness of the effect. It is the universality. Pound and Rebka were not creating gravitational time dilation in their laboratory. They were measuring it. It was already there. It has always been there, in every room, between every floor and ceiling, in every building ever constructed on the surface of this planet, since long before human beings invented the concept of a clock. The universe was always doing this. We simply built instruments sensitive enough to confirm it. General relativity did not become true when their measurement came out right. It was already true, in the kitchen of whoever first built that building, in the ground beneath every city that has ever existed, tonight, in the room where you are resting. The NIST experiment in Boulder in 2010 took the Pound-Rebka result and made it more intimate in a way that I find almost uncomfortable, in the best sense. Pound and Rebka needed a 22-meter building and had to push the limits of 1950s-era nuclear physics to make their measurement. The NIST team, working with optical atomic clocks roughly 1,000 times more precise than anything available in the post-war era, could do something that sounds like a setup for a joke. They ran 2 clocks side by side, confirmed they agreed, raised one of them 33 centimeters, about a foot above the other, and measured the difference. The higher clock ran faster. The fractional difference was approximately 4 parts in 10 to the 17th power, consistent with the prediction of general relativity for that height difference on Earth. They also measured the velocity effect. A clock moved at the speed of a relaxed walk, about 36 kilometers per hour, ran measurably slower than a stationary one. The results matched Einstein's equations, both the gravitational and the velocity effects, within the precision of their instruments. No corrections were needed, no modifications to the theory. The equations from 1905 and 1915 described, to the available precision, what was happening between 2 clocks separated by 1 foot on a laboratory table at the beginning of the 21st century. Take a moment with this before we go further. Not the numbers, the geography of it. The floor where you're lying and the ceiling above you are in different gravitational potentials. The difference is real, physical, and ongoing. Your head and your feet are aging at different rates, negligibly different, immeasurably different by any biology or any clock you own. but different in a way that the laws of physics would recognize instantly. The universe maintains this distinction continuously, without effort, without awareness, as a matter of its basic geometry. And if you could scale that geometry, if you could take the ratio between floor and ceiling and apply it to a gravitational field 1 billion times stronger, you would not get a negligible difference. You would get something that changes everything. Scott Kelly and Mark Kelly are identical twins, born on February 21, 1964, in New Jersey. Both became U.S. Navy test pilots. Both became NASA astronauts. Both flew space shuttle missions. Their genetic material is as close to identical as two separate human beings can be, which made them the perfect subjects for what NASA called the twin study. Scott would spend approximately a year on the International Space Station, while Mark stayed on Earth as the control subject, and researchers would compare the biological effects of long-duration spaceflight in as close to a controlled experiment as human beings ever get. The twin study results, published in the journal Science in 2019, covered a wide range of biological measures: changes in gene expression, telomere length, cognitive function, gut microbiome composition, cardiovascular fitness, vision. The paper ran to dozens of pages and is one of the most comprehensive biological profiles of a single spaceflight mission ever produced. But there is a physical fact embedded in Scott Kelly's mission that the biology paper didn't focus on, because in biological terms it is too small to register. In physics terms, it is everything. Scott spent 340 days aboard the ISS at an altitude of approximately 408 kilometers, moving at roughly 7.7 kilometers per second. At that velocity, special relativity predicts his clocks would run slower than Mark's on Earth by about 28 microseconds per day. But the ISS is also farther from Earth's gravitational center than the ground, a higher gravitational potential, and general relativity predicts that clocks there run faster by about 4 microseconds per day. The net, Scott's clocks ran slower by approximately 24 microseconds per day. Over 340 days, that accumulates to roughly 8 milliseconds. When Scott Kelly landed in Kazakhstan in March 2016, he was physically, biologically, measurably 8 milliseconds younger than he would have been had he stayed on the ground. 8 milliseconds younger than his twin Mark. Two brothers, the same genes, the same starting point. And time passed differently for each of them because one was moving faster and farther from Earth's center than the other. 8 milliseconds is nothing in a human life. It will never accumulate to anything noticeable by any biological measure, but the principle it demonstrates does not stop at 8 milliseconds. It scales. An astronaut moving at 1% of the speed of light, instead of 1/10,000th, would not return 8 milliseconds younger. They might return years younger. The physics is the same physics, the same equations, the same mechanism. The Kellys are proof of concept at a modest scale. The universe applies the same logic, without scaling limit, all the way to the event horizon of a black hole. Every black hole in the observable universe was born from something. The stellar mass black holes that gravitational wave observatories detect when they collide began, billions of years before their merger, as stars. Not small ones. But before we get to the physics of how they form, I want to tell you about a bet. In 1974, Stephen Hawking, whose work on black hole thermodynamics we'll return to later in the night, made a wager with his colleague and friend Kip Thorne. The subject of the bet was Cygnus X-1, a powerful X-ray source discovered in 1964, located roughly 6,000 light-years from Earth, now understood to be a black hole in a binary system with a blue supergiant companion star called HDE 226868. By the early 1970s, the evidence that the compact object in Cygnus X-1 was a black hole was accumulating. Its mass, inferred from the companion star's orbital motion, appeared to exceed the maximum mass that any known form of matter could support against gravitational collapse. It looked like a black hole. Hawking bet against it. Not, he later admitted, because he thought the evidence was wrong, but as what he called an insurance policy. If black holes didn't exist, he'd at least win the bet. Thorne bet that it was a black hole. In 1990, as measurements of Cygnus X-1's mass became increasingly precise, the compact object now understood to have a mass of roughly 15 solar masses, well above the maximum for a neutron star. Hawking conceded. He traveled to Thorne's office and signed a framed copy of their wager, acknowledging in his own hand that Cygnus X-1 was a black hole. The most famous concession in the history of theoretical physics, made by one of the people most responsible for our understanding of the objects being conceded. This is how black holes went from mathematical solutions to confirmed physical reality. Through argument, through measurement, through the slow accumulation of evidence that eventually even the most celebrated skeptics could not dispute. And the physics that produces them is, in its way, as dramatic as the objects themselves. Stars with initial masses roughly 8 to 25 times that of the Sun live shorter and more violent lives than a star like the Sun. They burn through their hydrogen fuel in millions rather than billions of years, and when their cores exhaust that fuel, the outward pressure of nuclear fusion that has been holding them up against gravity for their entire lives stops. The core collapses in less than a second, a fraction of a second in fact, reaching densities so extreme that protons and electrons are pressed together to become neutrons. The collapse bounces. The outer layers of the star, falling inward at a significant fraction of the speed of light, hit the rebounding core and are thrown outward in a supernova, briefly outshining the entire galaxy the star belongs to, emitting as much energy in a few seconds as the Sun will produce in its entire 10 billion-year lifespan. What remains is a neutron star, a sphere roughly 20 kilometers across, containing more than a solar mass of material, so dense that a teaspoon of it would weigh approximately 4 billion tons on Earth. Time at the surface of a neutron star runs measurably slower than time at a distance. The gravitational time dilation is real, detectable in the timing of pulsars. For stars more massive than roughly 25 solar masses, the core remnant after collapse exceeds the Tolman-Oppenheimer-Volkoff limit, approximately 2 to 3 solar masses, above which no known force, including the quantum pressure that holds neutron stars apart, can resist gravity. The collapse continues. Mass concentrates into a region so curved that the escape velocity at a certain distance equals the speed of light. Within that distance, nothing escapes. That distance is the Schwarzschild radius. The surface it describes is the event horizon. The region it encloses is a black hole, and Hawking's signed concession is on the wall to prove it. The event horizon is one of the most precisely defined boundaries in all of physics, and one of the most conceptually difficult to hold clearly in mind. It is not a wall. It has no surface, no density, no temperature that you could detect with any instrument as you approached or passed through it. The event horizon is defined entirely by what it implies about the future. Once you have crossed it, the mathematics of general relativity guarantee that every possible future trajectory, every path through time you could take, leads inward toward the singularity, not because of a force pushing you, not because of any boundary you have struck, but because the geometry of space-time inside the horizon is such that what we would normally call forward in time points inward. The singularity is not a place in space that you move toward. It is a moment in time that you move toward, the same way you move toward tomorrow, regardless of what direction you face. Inside the event horizon, you cannot avoid the singularity for the same reason you cannot avoid next Tuesday. For a non-rotating black hole described by the Schwarzschild solution, the simplest mathematical case, the event horizon is a sphere. Its radius is given by a compact formula, 2 times the gravitational constant times the mass of the black hole, divided by the square of the speed of light. For a black hole of 10 solar masses, that radius is approximately 30 kilometers. The event horizon is a sphere 60 kilometers across, smaller than many cities. The Sun currently has a radius of 700,000 kilometers. To compress 10 solar masses into a sphere 30 kilometers in radius is a degree of compression that resists ordinary visualization. The atomic structure of matter, the electromagnetic repulsion between electrons, the quantum pressure of degenerate particles, all of these are utterly overwhelmed. But the radius scales simply with mass. Double the mass, double the radius. And for the supermassive black holes that sit at the centers of most large galaxies, with masses of millions or billions of solar masses, the event horizon grows to sizes that are no longer small by any measure. The black hole at the center of the Milky Way, Sagittarius A, with a mass of 4 million suns, has a Schwarzschild radius of about 12 million kilometers, roughly 17 solar radii. The black hole at the center of M87, with a mass of 6.5 billion solar masses, has an event horizon spanning roughly 40 billion kilometers, approximately the diameter of the orbit of Neptune, multiplied by 3. If M87's black hole sat where our Sun sits, its event horizon would enclose every planet from Mercury outward past Neptune. The entire planetary solar system, everything from the innermost rocky planet to the icy giants, would lie inside a region from which nothing could return. And the size of the event horizon determines, in a way that has profound physical consequences, what it is like to fall through it. On April 10, 2019, at simultaneous press conferences held on 4 continents, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow. The target was M87, 53 million light-years from Earth in the constellation Virgo. The image showed a glowing, asymmetric ring of emission, superheated gas and plasma, orbiting the black hole at a significant fraction of the speed of light, surrounding a dark central region, the shadow, the area from which light either cannot escape or is captured into orbits that eventually fall inward. One side of the ring was noticeably brighter than the other. Material on the side rotating toward us is Doppler boosted. Its light increased in intensity, while material on the receding side is dimmed. These brightness differences were predicted. They showed up in the image exactly as the physics required them to. The Event Horizon Telescope is not a single instrument. It is a network of radio telescopes distributed across the Earth, in Hawaii, Arizona, Mexico, Chile, Spain, Greenland, and the South Pole, linked through a technique called very long baseline interferometry to simulate a telescope the diameter of the entire planet. The angular resolution this achieves is equivalent to reading the date on a coin in New York City while standing in Los Angeles. The data from each participating telescope is recorded on hard drives and physically transported to correlation centers where it is combined. In the case of the Antarctica station, the data had to wait for the end of polar winter before it could be shipped, which means the South Pole's contribution to the first ever image of a black hole traveled on a supply plane months after the other data had already been processed. Then, on May 12, 2022, the EHT released its second major result, an image of Sagittarius A, the black hole at the center of our own galaxy, 27,000 light-years away. Imaging SGR-A was technically more challenging than imaging M87. Because it is smaller and less massive, material in its accretion disk completes a full orbit in minutes rather than days, meaning the disk's appearance changes on timescales shorter than a single observing session. The team had to develop new techniques to average images taken across multiple nights while accounting for the variability, as well as for the scattering caused by the interstellar plasma between Earth and the galactic center. The resulting image showed the same structure, a bright emission ring around a dark shadow, matching general relativity's predictions. Both images, taken of objects separated by 53 million light-years and of vastly different masses, confirmed Einstein's equations written down in 1915. The theory has now been tested at scales ranging from a foot-high laboratory shelf to a 6.5 billion solar mass black hole 53 million light-years away. It has not failed. We don't need to look as far as M87 to find direct, measured evidence of extreme time dilation near a black hole. We can look at our own galaxy's center, 27,000 light-years away, and watch individual stars move. For more than 3 decades, 2 groups of astronomers, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, one led by Andrea Ghez at UCLA, tracked the orbits of stars in the immediate vicinity of Sagittarius A using infrared telescopes equipped with adaptive optics, systems that measure atmospheric turbulence in real time and adjust the telescope mirror hundreds of times per second to correct for the blurring it introduces. The galactic center is invisible in ordinary light, obscured by dust along the line of sight. But in infrared wavelengths, the stars can be seen and their motions tracked with extraordinary precision over years and decades. The star called S2, designated S02 in the Euclid group's notation, orbits Sagittarius A with a period of approximately 15 to 16 years, following an ellipse that brings it within roughly 120 astronomical units of the black hole at closest approach. 120 astronomical units is about 120 times the distance from the Earth to the Sun, approximately 18 billion kilometers at periapsis. At that closest point, S2 reaches orbital velocities of approximately 7,650 kilometers per second, about 2.5% of the speed of light. In 2018, S2 completed a periapsis passage, and the Gravity Collaboration, a European team using the Gravity Interferometric Instrument at the Very Large Telescope in Chile, measured the gravitational redshift of S2's light at closest approach. The light emitted by S2, as it swept through the deepest point of Sagittarius A's gravitational field, was redshifted, its frequency reduced, its clocks running slower, by exactly the amount that general relativity predicted for a star moving that fast in that gravitational field. This was a direct measurement of gravitational time dilation at the center of the Milky Way, not an inference, not a model, a measurement of light from a specific star at a specific point in its orbit, in a specific gravitational field, compared to the prediction of a specific set of equations, and the equations were right. Reinhard Genzel and Andrea Ghez received the Nobel Prize in Physics in 2020 for this work, shared with Roger Penrose for his earlier mathematical proof that singularities must form inside black holes under general conditions. Now let me bring you to the edge itself, not because there is anything dangerous in imagining it, but because the contrast between what happens at a small black hole and what happens at a large one is one of the most important and least discussed facts in the physics of these objects. And understanding it is essential to the strangest part of tonight's story. You are in a spacecraft falling toward a black hole. Scenario 1, a stellar mass black hole of 10 solar masses. Event horizon radius, 30 kilometers. As you fall, nothing unusual happens at first. You are in free fall, weightless, the same weightlessness astronauts on the space station experience, because the black hole's gravity accelerates every part of you equally, and there is no net differential force for your body to feel. But as you draw closer, the tidal gradient increases. The near side of your body is being pulled meaningfully harder than the far side. This stretches you along the direction of fall, lengthwise, toward and away from the black hole. Simultaneously, the sides of your body are compressed inward toward the line connecting you to the singularity. Physicists call this tidal force, and the popular literature gave it the name spaghettification, a word coined by someone with a sense of humor that apparently survived peer review. For a 10 solar mass black hole, these tidal forces become lethal well before you reach the event horizon. The physics is unambiguous. A human body would be torn apart before ever crossing the boundary. But now, scenario 2. Same fall, same physics, different black hole, 6.5 billion solar masses, the mass of M87. The event horizon is now 20 billion kilometers in radius. The singularity is 20 billion kilometers from the horizon. The tidal force at the event horizon, the difference in gravitational pull across the length of a human body, about 2 meters, is vanishingly small because the gradient of the gravitational field is extremely shallow at that enormous distance from the singularity. A human falling through the event horizon of M87 would feel nothing, no stretching, no compression, no heat, assuming they are not falling into the accretion disk's material, no sensation of any kind that would be new or alarming. The moment of crossing, the threshold past which no return is possible, the boundary that separates the observable universe from a region permanently cut off from it, would feel, to the person crossing it, like continuing to fall through open space. The size of the black hole determines not just the location of the event horizon, but the quality of the experience of crossing it. This is the counterintuitive core. The larger and more massive the black hole, the gentler the experience at the horizon, and for the largest black holes we know of, the crossing is perfectly, absolutely, deceptively unremarkable. Let me pause here for a moment and simply sit with what we have established. We began with a clock on a shelf in Colorado, measuring time dilation over a foot of height. We have arrived at the event horizon of a supermassive black hole, where that same physical mechanism, the effect of gravity on the flow of time, has become absolute. The connection between those two things is not metaphorical. It is mathematical, continuous, and exact. The same equations that describe the foot of height experiment describe the event horizon. The physics does not change quality along the way from modest to extreme. It simply scales. And the strangest part of that scaling, the thing I keep returning to, is the silence of it. You are resting somewhere right now. Gravity is pulling every part of you downward at roughly 9.8 meters per second squared, and the surface beneath you is pushing back with exactly enough force to hold you still. In that gravitational field, your body is a clock. Every heartbeat, every chemical reaction in your cells, every oscillation of every atom that comprises you is a timekeeping mechanism. And all of those mechanisms are running at the rate that your position in Earth's gravitational field and your velocity through space requires. You cannot feel this rate. There is no sensation that corresponds to the speed at which time is passing. You can only feel the present moment, which is always, in every reference frame, at every gravitational potential, simply now. The rate is invisible from the inside. It only becomes visible from the outside, in comparison, in the gap between one clock and another, between one twin and a sibling, between a traveler and the world they left. Let your breathing slow a little. Let this particular now be exactly what it is. Here is the paradox that troubled physicists for decades after black holes were accepted as real objects. When we say that an observer falling into a large black hole crosses the event horizon without any unusual sensation, we mean something specific. In that observer's reference frame, in their own proper time, the crossing is uneventful. But an observer, watching from far outside the horizon, sees something completely different. And the two descriptions, placed side by side, look at first like they are contradicting each other. From the outside, as an object falls toward a black hole, the light it emits takes progressively longer to climb out of the deepening gravitational well and reach the distant observer. Near the event horizon, this effect is not gradual. It is asymptotic. The time dilation factor at the horizon approaches infinity. From the distant observer's perspective, the infalling object slows. Its light redshifts, frequency dropping, wavelength stretching, the signal dimming as it becomes increasingly difficult to detect. In the mathematical limit, the object appears to freeze at the horizon, hovering there indefinitely, becoming redder and dimmer until it fades entirely from detectability. It never, in the outside observer's time, actually crosses. From the infalling observer's perspective, they cross in a finite amount of their own time. The horizon passes, their clocks tick normally, by their own experience, and they continue falling, toward the singularity, toward the end of what can exist inside that geometry. Both of these descriptions are valid. Neither is wrong. They are different slices through the same four-dimensional space-time geometry, seen from reference frames that cannot share a common now once the infalling observer approaches the horizon. The concept of simultaneity, the idea that two events can be described as happening at the same time, loses absolute meaning in general relativity, and near a black hole this loss is not a small correction, but a fundamental feature of the geometry. There is no neutral referee position from which a single definitive timeline can be constructed. The outside observer's frozen image and the infalling observer's uneventful crossing are not in contradiction. They are different truths, each valid within its own reference frame, neither accessible to the other. This is philosophically demanding in a way that takes time to absorb properly. We are accustomed to thinking of the universe as having one history, one sequence of events that, in principle, everyone could agree on, given sufficient information. General relativity removes this assumption. The universe does not maintain a master timeline. It maintains local timelines, the proper time of each observer, ticking at the rate their location and velocity requires. And these local records cannot always be woven into a single global story without choosing a perspective and accepting that other perspectives will tell a different but equally valid version. I want to stay with the experience of the infalling observer because I think it is the most important and least examined aspect of what we have been building toward all night. Suppose you have a spacecraft capable of reaching Sagittarius A, the 4 million solar mass black hole at the center of the Milky Way. You travel there. You establish an orbit in the strong gravitational field outside the event horizon, close enough that time dilation is significant, but not so close that the orbit is unstable. You remain there for what your clocks record as 1 year. You eat, you sleep, you live the ordinary business of being a person, because time in your reference frame moves at the same rate it always has, 1 second per second, by the only measure available from inside your own experience. You have no sensation of time moving slowly. There is no heaviness to the hours, no resistance in the moments. You complete your year. You return to Earth. But when you arrive, the calendar says you have been gone for far longer than a year. How much longer depends on exactly how deep in the gravitational field your orbit was. It might be a decade. It might be several decades. People you left behind have aged. Children have grown. Some of those you knew have died. The world has moved forward at its own clock's rate, which was running faster than yours the entire time you were near the black hole. And you, stepping back into that world, feel as though you have been gone for exactly 1 year. Because you have been, by your clock, by your biology, by every measure available from within your reference frame. You are 1 year older. The world is 30 years older. The gap between those two numbers is real on both sides. Neither of you kept the wrong time. You simply kept time in different gravitational fields. You would not have felt the dilation while it was happening. This cannot be emphasized enough. There is no sensation of time moving slowly near a black hole. Time in your reference frame always moves at 1 second per second. That is what a reference frame is. The dilation is relational. It exists only in the difference between your clock and another clock. It is only readable in comparison, on return, in the gap between where you left and where everything else arrived. Now extend this to the crossing itself. Suppose you do not stop at a safe orbit. Suppose you fall through the event horizon of a large enough black hole, one of the gentle crossings I described. You pass through. Your clocks continue ticking. Your thoughts continue occurring in sequence. The present moment remains immediately present, and at the crossing, the one-way nature of what has happened becomes complete. You cannot signal outward. Nothing you transmit can climb out. From the outside universe's perspective, you have frozen at the horizon, red-shifting into invisibility, suspended in an apparent stillness that will never resolve. From your perspective, you are simply falling forward in time, as you have always been, as all of us always are, toward what comes next, with no organ to sense what rate that passage has reached. What you would never feel is the most important crossing of your existence. The border between the universe and whatever lies beyond passes through you without announcement, and then you continue, in your own time, toward what awaits further in. In 2012, 4 theoretical physicists published a paper that generated something unusual in academic physics: genuine alarm. Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, collectively abbreviated as AMPS, showed that 3 foundational principles of physics cannot simultaneously hold at the event horizon of a black hole. And if 2 of those principles hold, the third, the peaceful, uneventful crossing I have just described, might not be peaceful at all. The 3 principles in conflict are the equivalence principle, which is the foundation of general relativity, and which says a freely falling observer crosses the horizon without experiencing anything locally unusual; unitarity, the quantum mechanical requirement that information is never permanently destroyed, that the evolution of quantum states is always reversible in principle, and the principle that Hawking radiation, which we will discuss shortly, carries information away from the black hole in a way that allows the black hole's quantum state to eventually be recovered as it evaporates. AMPS showed, through careful analysis of the entanglement structure required for information to escape via Hawking radiation, that the quantum fields at the event horizon cannot simultaneously satisfy all 3 requirements. Something has to break, and if it is the equivalence principle that breaks, then the infalling observer does not experience a quiet crossing. They hit a wall of high-energy radiation the instant they reach the horizon, a so-called firewall, and are destroyed immediately. This paper generated years of intense debate, and it deserves to be said clearly. The firewall paradox is not a prediction that you would be destroyed at the event horizon. It is a demonstration that our current theories, taken together, produce an inconsistency that must be resolved before we can say what actually happens. It is physics identifying its own limits. In 2013, Juan Maldacena and Leonard Susskind proposed a resolution they called ERED-EPR, the conjecture that quantum entanglement between particles, Einstein-Podolsky-Rosen pairs, and the geometric connections between spacetime regions, Einstein-Rosen bridges, or wormholes, are the same physical phenomenon described in different languages. If this is right, the entanglement required for Hawking radiation to carry information is not something external to the black hole's geometry. It is the geometry. The firewall paradox would dissolve because the question it poses would be based on a false separation. But ER.EPR is a conjecture, not a theorem. It is supported by evidence from holographic dualities and by its consistency with known physics, but it has not been derived from first principles in a way that settles the question completely. As of today, we do not know what an infalling observer would experience at the event horizon of a black hole. General relativity says nothing unusual. Quantum mechanics, under certain interpretations, says something more complicated. The universe is being asked to reconcile its 2 most successful theories at the one location where they are most directly in conflict, and it has not yet answered in a way both can agree on. That open question is not a failure of physics. It is physics being honest about where it currently stands. In 2014, Christopher Nolan's film Interstellar attempted something that no major motion picture had done: depict a black hole using physics rather than imagination. Kip Thorne, one of the central figures in the development of general relativity as a research program, a key architect of the LIGO gravitational wave detector, and a recipient of the 2017 Nobel Prize in Physics, served as the film's executive producer and scientific advisor. Thorne provided the visual effects company, Double Negative, with equations from which they built rendering software called DSCAR, Double Negative Gravitational Renderer. This software traced the paths of individual light rays through the curved space-time geometry near a rotating black hole, computing at each point how that geometry bent and redirected the light. The result, the black hole called Gargantua in the film, was not an artist's interpretation. It was a computation. What surprised even Thorne was the appearance of the accretion disk. In prior artistic depictions, the disk appeared around the equator of the black hole, the plane of orbiting material, extending outward to the sides. But the gravitational lensing of a massive black hole bends the light from the near and far edges of the disk over and under the event horizon, so that an observer near the black hole would see glowing material appearing above and below as well, wrapped around by the curvature of space-time into a complete, distorted halo surrounding the shadow on all sides. When the Event Horizon Telescope released its image of M87 in 2019, the resemblance to Gargantua was immediately striking. The computational approach Thorne had provided for a Hollywood production had, in effect, been confirmed by a network of telescopes spanning the Earth. Thorne published the lensing results as a scientific paper in Classical and Quantum Gravity in 2015, noting that the production had inadvertently generated scientifically useful new visualizations of gravitational lensing in the process of making a film. The planet Miller, the one in the film where 1 hour of surface time equals 7 years elsewhere, represents the human-scale consequence of extreme gravitational time dilation pushed to its physical limit. For that ratio to be achievable, Gargantua would need to be a maximally spinning Kerr black hole, rotating at essentially the maximum rate general relativity permits, and Miller's orbit would need to sit at or extremely near the innermost stable circular orbit, the minimum distance at which a stable orbit is possible before the object spirals inward. Thorne worked through the mathematics with care. A spin parameter approaching the theoretical maximum, combined with an orbital radius at the innermost stable circular orbit, allows a time dilation factor of approximately 7. The scenario sits at the very edge of what general relativity permits, requiring conditions that are almost impossibly difficult to maintain, but it requires no new physics. The equations that Pound and Rebka tested in a 22-meter building, applied at their extreme limit, produce the gap between two clocks that becomes, in the film, the gap between a daughter's childhood and her adulthood. A scene that lands not because it is science fiction, but because the science is real. For most of the 20th century, black holes were understood to be permanent. Once mass crossed the event horizon, the universe had lost access to it. The black hole would persist indefinitely, growing slowly as it consumed surrounding matter, never returning anything to the cosmos. They were the universe's one-way structures, indefinitely stable, without exit, without end in time. Then in 1974, Stephen Hawking showed that black holes are not completely black. Using quantum mechanics applied to the space-time near an event horizon, he demonstrated that black holes must emit thermal radiation, now called Hawking radiation, with a temperature inversely proportional to their mass. The mechanism is indirect and draws on the quantum structure of the vacuum. In quantum mechanics, empty space is not truly empty, but populated by pairs of virtual particles that constantly appear and annihilate. Near the event horizon, the gravitational field can separate a pair before annihilation occurs. One member falls inward, the other escapes outward as real radiation. The energy for this process comes, in the bookkeeping of conservation laws, from the black hole's mass, which decreases slightly with each such event. Over time, integrated across all such events, the black hole radiates and very slowly loses mass. It evaporates. The temperatures involved for the black holes we can observe are almost incomprehensibly small. A stellar mass black hole of 10 solar masses radiates at approximately 6 billionths of a Kelvin. the cosmic microwave background, the ambient thermal radiation that fills all of space, the faint electromagnetic glow left over from the Big Bang, is approximately 2.7 Kelvin. Hawking radiation from a 10 solar mass black hole is roughly 450 million times colder than the ambient temperature of the universe. It is completely and permanently undetectable against that background. The time for such a black hole to evaporate completely is approximately 2 × 10 to the 67th years for a solar mass object, a number so vastly larger than the current age of the universe that calling it a timescale is an abuse of the word. Black holes are not permanent in principle. They are as close to permanent as anything in the observable universe has managed to be. Hawking radiation has never been directly observed. No instrument currently exists or can be envisioned that would be sensitive enough to detect it from any astrophysical black hole. It remains one of the most important theoretical results of the 20th century, derived from first principles, supported by independent derivations, using different mathematical approaches, widely accepted as correct in the physics community, and one of the least experimentally constrained. It sits exactly at the boundary between general relativity and quantum mechanics, which is the reason it is important. It is our best current glimpse into the regime where both theories must apply simultaneously, and where they must eventually be reconciled. In the constellation Canes Venatici, the hunting dogs, there is an object designated 2ON 618. It is a quasar, the luminous nucleus of a distant galaxy, its extreme brightness powered by material falling at high rates into an active supermassive black hole. The light we receive from it today left its source approximately 10.4 billion years ago, when the universe was roughly 3 billion years old, less than a quarter of its current age. What we see is a record of the universe's active, turbulent youth. And at the center of TON 618 is one of the most massive black holes currently known, approximately 66 billion solar masses. The Schwarzschild radius of TON 618, the radius of its event horizon, works out to approximately 1,300 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. TON 618's event horizon has a radius 1,300 times that distance. Neptune, the outermost known planet, orbits the Sun at approximately 30 astronomical units, Pluto at roughly 40. The inner edge of the Oort cloud, the vast spherical shell of comets and icy bodies that marks the outermost boundary of the Sun's gravitational influence over small bodies, begins at roughly 2,000 astronomical units. TON 618's event horizon extends to 65% of that distance. If TON 618 occupied the position of our Sun, its event horizon would engulf Neptune's orbit and extend well into the outer solar system. Every planet, every asteroid belt, the entire region of the solar system where human spacecraft have traveled, would lie inside a region from which nothing could escape. The tidal forces at the event horizon of a 66 billion solar mass black hole are negligible across the scale of a human body. The singularity is so far from the horizon, 1,300 astronomical units, that the gradient of gravity is exceptionally gentle at the boundary. A person falling through TON 618's event horizon would experience no unusual sensation at the crossing. They would be inside the largest known event horizon in the observable universe, enclosed in a region of space-time representing 66 billion times the mass of the Sun, from which no signal and no light can ever escape outward. And they would feel, in that specific moment, nothing different from falling freely in empty space. The universe is sometimes strange in quiet ways. On September 14, 2015, at 5:51 in the morning, Eastern Daylight Time, a detector in Livingston, Louisiana, and a detector in Hanford, Washington, simultaneously registered a signal. The signal lasted just over a fifth of a second. It was a tiny oscillation in the lengths of each detector's 4-kilometer arms, a displacement 1,000 times smaller than the diameter of a proton. It was the faintest signal ever, directly detected by any human instrument. And it was caused by 2 black holes, one roughly 29 solar masses, one roughly 36, that had been spiraling toward each other for billions of years, finally merging into a single object of approximately 62 solar masses, somewhere approximately 1.3 billion light-years from Earth. The missing 3 solar masses were converted directly into gravitational waves, rippling outward through the fabric of space-time itself at the speed of light. Those ripples, 1.3 billion years later, attenuated to almost nothing but not quite nothing, passed through the Milky Way, through the Sun, through the Earth, and briefly stretched and compressed the geometry of space inside those 2 L-shaped detectors by a fraction smaller than an atomic nucleus. LIGO, the Laser Interferometer Gravitational Wave Observatory, was built specifically to detect this, distortions in the geometry of space-time caused by passing gravitational waves, measured by comparing the travel time of laser light in 2 perpendicular tunnels, 4 kilometers long. The detection was confirmed by the signal appearing at both detectors 7 milliseconds apart, consistent with the known travel time of a gravitational wave at the speed of light between Livingston and Hanford. It was announced publicly on February 11, 2016. It confirmed a prediction Einstein had made in 1916, 1 year after completing general relativity. He had doubted the effect would ever be detectable. He was wrong about that. LIGO, working with the Virgo detector in Italy and Kagra in Japan, has since detected well over 100 gravitational wave events, mergers of black holes with black holes, neutron stars with neutron stars, and mixed pairings. Each waveform encodes, in its shape as it evolves across the fraction of a second of the merger's final stages, the masses and spins of the objects involved, and the orbital dynamics they followed under the equations of general relativity for their entire inspiral. Each detection is a measurement of the geometry of space-time at a specific moment, from an event that occurred millions or billions of years before any human being existed. In one remarkable case, GW 170817, a neutron star merger detected in August 2017, the gravitational wave signal was accompanied by electromagnetic emission, detected across the full spectrum by dozens of observatories worldwide, confirming that neutron star mergers produce the heavy elements, gold, platinum, uranium, that exist in the universe. The gravitational wave detections are measurements of time, of the curvature of space-time, of the most extreme objects doing the most extreme things, and they keep confirming the same equations that describe the difference in clock rates between your floor and your ceiling. We are in the later part of the night now. The questions we have been carrying have grown larger as we have gone, which seems right. The right kind of question opens outward, makes more room rather than less, and what we have been exploring tonight does exactly that. Let your breath settle a little more. Let the weight of your body press into whatever is holding it, and let that holding be enough. You have been, for this entire conversation, a clock in a gravitational field. Every moment of this night, time has been passing for you at the rate that Earth's gravity and your velocity through space requires, a rate determined entirely by your specific position in the universe, by the mass of the planet beneath you, and the geometry of the space-time you are moving through. You cannot feel this rate. No one can. We feel only the present, which is always, from inside, simply now. The rate at which that now arrives is invisible to us, as it is invisible to every observer in every reference frame everywhere in the universe. That invisibility is what I find most profound tonight. Not the extremity of the black hole physics, not the scale of the numbers, not even the open paradoxes at the edge of what we know, though all of those are remarkable. What stays with me is the quietness of it. The fact that the most fundamental property of your existence, The rate at which you move through the one dimension that flows only forward is something you cannot perceive directly. Only compare, only measure against another clock, only reckon with upon return. The rate is always, from inside, simply the present. The information paradox is perhaps the deepest unresolved problem in theoretical physics, and it begins with a question that sounds straightforward. When matter falls into a black hole, what happens to the information it carries? In quantum mechanics, information is always conserved. The quantum state of any system evolves according to equations that are reversible in principle. Given the exact final state of a quantum system, you can reconstruct every prior state. No information is permanently lost. This principle, unitarity, is foundational to quantum mechanics, in the same way the equivalence principle is foundational to general relativity. Its violation would require rebuilding the theory at the most basic level. But when matter falls into a black hole, and the black hole subsequently evaporates through Hawking radiation, the radiation appears to carry no specific information about what fell in. It is thermal, essentially random, like the radiation from any warm object, with no detectable signature of the specific particles and arrangements that cross the horizon. The final state of the Hawking radiation does not seem to encode the initial state of the infalling matter. Information appears to be lost. This violates unitarity. Either information is destroyed, contradicting quantum mechanics, or it escapes, encoded in the Hawking radiation in a way that current calculations do not reveal. Hawking initially believed information was simply lost. He conceded this position in 2004, acknowledging evidence from string theory, particularly the ADS-CFT correspondence, a precise mathematical equivalence between a theory of gravity in a specific curved spacetime and a quantum field theory living on its boundary, strongly suggested that information is preserved. If the boundary quantum theory is manifestly unitary, and if it is truly equivalent to the bulk gravity theory, then information must be conserved in the bulk as well. But the mechanism by which this happens, how the specific information encoded in matter that fell through a one-way boundary could be recovered from the radiation emitted before and after, is not understood by any framework we currently possess. The information paradox is not a peripheral technical problem. It sits at the exact intersection where general relativity and quantum mechanics come into direct and irreconcilable conflict. Whatever resolves it will not merely close a gap in the literature, it will require physics more fundamental than either of the two theories it unifies. A framework that tells us what space-time is made of at the quantum scale, how geometry and information are related at the deepest level, and almost certainly reveals aspects of reality not currently visible in either framework operating independently. Here is an honest account of what we do not know, stated as plainly as I can manage. We do not know what is physically occurring at the center of a black hole. General relativity predicts a singularity, a point of infinite density, and simultaneously predicts that its own equations break down at that point. The singularity is not a physical description. It is a marker for the edge of the theory's validity. A complete theory of quantum gravity, which would be required to describe physics at the densities encountered near a singularity, does not currently exist. The interior of a black hole, past some scale near its center, is genuinely unknown. We do not know whether Hawking radiation is real in the sense of being experimentally confirmed. The theoretical prediction is robust, derived from careful quantum field theory in curved spacetime, supported by multiple independent derivations, widely accepted as correct. But it has never been detected. No evaporating black hole has been observed. No Hawking photon has been measured. We believe it happens. We cannot yet show it. We do not know the resolution of the firewall paradox, and therefore, we do not know what an infalling observer would actually experience at the event horizon of a black hole. The equivalence principle says nothing unusual. Quantum mechanics, under certain reasonable assumptions, says something else entirely. We do not know which principle the universe chooses when they conflict. We do not know whether primordial black holes formed in the early universe, and if so, whether they contribute to the dark matter whose gravitational effects are detected everywhere in the cosmos, but whose physical nature remains unidentified after decades of dedicated search. LIGO's detection of black holes in the 30 solar mass range, masses not easily explained by standard stellar evolution models, briefly reinvigorated this possibility. The question remains open. These are not footnotes at the back of a field that has otherwise finished its work. They are the current front lines, where the best-equipped researchers in the world are showing up every day. The openness of the questions is not a failure. It is the field doing what science is supposed to do, locating its own edges with precision and honesty, so that the next generation of work has a clear direction. Here is what I want to leave you with, as the night has reached its quieter hours, and whatever sleep is waiting for you has drawn a little closer. Time is real. It is physical. It responds to the geometry of the space around it, bending when mass bends space-time, slowing when velocity increases, running faster at higher gravitational potential and slower at lower. At the surface of the Earth, where you are tonight, time is moving at a rate very slightly slower than it would move in intergalactic space, far from any significant mass. Your cells are aging at a rate determined by this specific gravitational potential, this latitude, this altitude, this position in the universe. This is not a metaphor. It is a measurement, confirmed by atomic clocks in basements and on shelves and aboard satellites, by the careful tracking of a single star orbiting the center of the Milky Way, by the timing of pulses from a rotating neutron star, by the navigation calculations running silently inside every device that knows where it is on Earth. And at the far end of what this means, at the place where gravity is not the quiet suggestion of a planet, but the absolute curvature of a singularity, enclosed in a one-way surface, time does not slow. It stops, in the eyes of any outside observer. It becomes frozen at the horizon, the infalling object suspended there in apparent stillness, red-shifting into invisibility, never, in any outside reference frame, actually crossing. The image is complete and final and permanent. Time, at that boundary, from the outside, has ended for that object. While inside, it falls. While inside, the present moment is as present as it has ever been, 1 second per second, the only rate that time ever has from inside a reference frame, as the universe outside ages in ways that will never be reported back across the threshold that has been crossed. The traveler continues in their own time toward what the geometry of that interior space requires, carrying their clock and their experience and their sense of an ongoing present into a region the rest of the universe will never reach. We live in a universe where the most permanent departure imaginable is undetectable from the inside, where the GPS satellites your phone relies on required Einstein's equations built into their hardware before they could work, where two brothers, one who went to space for a year and one who stayed on Earth, came back from that year at a real, physical, 8-millisecond difference, where raising a clock 1 foot off the floor changes the rate at which it ticks, where a star orbiting the center of the galaxy confirmed a century-old equation with a measurement of its own light, and physicists were awarded the Nobel Prize for listening. You are not outside this. You are a clock in a gravitational field, running at the rate your specific location requires, accumulating your particular version of time in the particular place in the universe where tonight finds you. The fact that you cannot feel the rate, that you feel only the continuous present, only the moment that is always now, is perhaps the most intimate and most strange thing in all of what we have explored. The strangeness is invisible from inside. It requires the outside view, the comparison, the reckoning, the return. And most clocks never have the reckoning. Most of us simply live in our own reference frame, in our own gravitational well, feeling each moment as simply this, and then this, and then this. That is enough. It is more than enough. In the most precise and literal sense available to physics, it is everything. Rest now. Let the hour carry you where it intends to go. Your clock is running correctly, at the exact rate that this specific location in the universe requires. No faster and no slower, perfectly calibrated to the curvature of space-time at this altitude and this latitude and this velocity. There is no other place in the cosmos where time is passing at precisely this rate. This rate belongs, uniquely and entirely, to right here, right now. Good night.